Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. So you can recall that in the last lecture we initiated a discussion on the estimation of parameters, right? And towards the end I had explained you that there are a couple of properties which are expected in a good estimator, because if these properties are present in those estimators, then we try to say that the estimators are good. So in this lecture I am going to talk about the property of unbiasedness, right. Well, out of the properties unbiasedness, consistency, sufficiency, efficiency, etc., there is no ordering, but I am simply trying to take the unbiasedness as the first property, not because of any ordering, because I have to choose one topic for this lecture. Okay. The first question comes, what is this unbiasedness? Forget about statistics, think about in a very simple way. Have you ever used this word unbiased in your life, day-to-day life? Answer is yes. Many times you say that, okay, this teacher is unbiased, or sometimes you say, no, this teacher is biased towards a particular student, or sometimes in our family also we say, okay, my parents are biased towards my younger brother or towards my elder brother or my sister. These types of sentences are very common. Now, in case if you try to understand and try to explain yourself, what do you really want to convey when you try to use this word unbiased or biased? For example, if there are two students in a class and suppose me as a teacher, what I try to do, that both the students are suppose making the same mistake in the examination in a question. And suppose out of 10 to one student I give suppose 7 marks, and I deduct 3 marks for the mistake, and to other student I give only 5 marks and I deduct 5 marks for the mistake. Now, what will be the comment of the students for me? They will say, okay, I am biased towards a student. That means, what would I have not done so that they cannot call me biased? The only thing is this, if I had given the same marks to both the students, means either 7 to both or 5 to both, then there should not be any problem. So that means whenever I am trying to deviate from the true value, I am trying to introduce a bias in the marks of my students. So now if you try to think in these lines and try to think about your estimator that is going to estimate the value of an unknown parameter of the population, what do you expect? You expect that the parameter which you want to estimate, which is actually really unknown, that you do not know, you are trying to know its value through a estimator which is a function of random variable, that is a statistic, and you want this value to be close to the true value. You do not want much deviation from the true value, right. So this is basically the idea about this unbiasedness character of an estimator. So let us try to begin our lecture and try to understand from the statistical point of view, how do we define this unbiasedness and how do we check that whether an estimator can be said to be an unbiased estimator of the unknown parameter, or it is a biased estimator of the unknown parameter. So let us begin our lecture. Okay, so now in case if you try to recall that you were trying to estimate an unknown parameter theta, and we had indicated by this theta hat, this is a value of theta obtained from the sample values, right, that you know. So, now and this theta hat is called as an estimator, right, and theta hat is also a statistic. So, this is a random variable. So, what we expect that an estimator should be close in some sense to the true value of the unknown parameter, and formally and statistically speaking, we say that theta hat is an unbiased estimator of theta if the expected value of theta hat is equal to theta. And if you try to understand what is the meaning of this is trying to say that the mean of the probability distribution or the mean of the sampling distribution of theta hat is equal to theta. And remember one thing, this property, the property of this unbiasedness, this is a finite sample property. Why I am calling it a finite sample property? Because in the next lecture I am going to talk about the property of consistency, and consistency will be a asymptotic property, means when the sample size become large. But when I say this finite sample property, that means it will hold true even when the sample size n is finite. This is what I mean. Okay. So, now I can introduce here the formal definition once again, that the point estimator theta hat is an unbiased estimator of the parameter theta if expected value of theta hat is equal to theta, right. So, and in case if this condition does not hold true, then we say that the estimator is not biased, but it is biased, and in that case the bias of theta hat is defined as like this, expected value of theta hat minus theta, right. This is called the bias of the estimator, and we will always be interested in knowing whether the estimator that we are using for estimating an unknown parameter of the population is an unbiased estimator of the parameter or not, and if it is a bias estimator, then what is the amount of bias, right, because if the bias is large, then possibly the estimator may not give us the good value of the unknown parameter theta, right. So, obviously when an estimator is unbiased, obviously the bias is 0, and the interpretation of this unbiased character is that we want or we expect that all the values of theta hat to be equally spread around the two sides of theta like this. If this is my here theta, then this value of these are the values of theta here on these two sides, right. Okay. And let me try to explain you that what is the meaning of expected value of theta hat is equal to theta. And I am trying to take a very simple example. This simple example will make you understand that what are we really going to do when we are trying to deal with the probability distribution. Suppose I have a population of only 3 values, say capital X1 equal to 1, capital X2 equal to 3 and capital X3 equal to 5. And now if you try to see what is the arithmetic mean of these 3 values, which is here 1 plus 3 plus 5 upon 3, which is equal to here 3. So, the population mean here is 3, and yeah, this you can say that this is unknown to us, right. Yeah, just for the sake of example, I am just taking these values, but definitely in practice this value will be unknown. So, I can just remove this value from here, means I can hide this value, so that will indicate as if we do not know. Now, suppose you want to know this value and you try to draw a sample of size 2. Now, there are 3C2 or say 3 choose 2 possible ways in which you can draw a sample of size 2 from a population of size 3, right. So, this is 3 choose 2 is equal to 3, right. So, now we want to estimate the unknown population mean by the sample arithmetic mean, right. And so, for that we try to choose here all the 3 possible sample and we try to find out the sample mean. So, if you try to take the first sample, suppose you are getting the values say 1 3, then the sample mean in this case will come out to be 1 plus 3 divided by 2, which is actually 2. And in case if you draw one more sample, so there are actually three possible samples, the values 1 3, 3 5 and 1 5. So, suppose if you try to draw second sample and suppose you get the value 3 5, then in this case the sample mean will come out to be 3 plus 5 upon 2, which is equal to here 4, and that is supposed indicated by SM2, sample mean 2. And similarly, if you try to take the units 1 and 5 in the sample, then the sample mean is going to be computed by 1 plus 5 upon 2, which is equal to 3, and that is going to be indicated by the indicator or the symbol SM3, sample mean 3. Now, try to do one thing, try to take the arithmetic mean of these sample means. So, we try to compute here SM1 plus SM2 plus SM3 divided by 3, that is 2 plus 4 plus 3 divided by 3, and this will come out to be here 3. So, now if you try to see what was this 3, this was your here this population mean that was unknown to us. So, you can see here that if you are trying to take all possible samples from the population, and in case if you are trying to find out the mean of all the means, and if this value comes out to be the same as the value of the population mean, then we say that our estimator is an unbiased estimator of the population mean. And if you try to see here, here you are trying to estimate the value of this population mean, which is actually here 3, you are trying to estimate it by the value 2 or 4 or by 3. So, you can see here that the difference between the estimated value here, these are your here estimated value, and the population mean, it is not going to be large. Well, in practice you are going to have only one sample. So, if you get this sample, you get here a sample mean 2. So, the deviation is only for 2 different 3. And if you are getting this suppose sample whose sample mean comes out to be 4. So, you can see here that the difference between 3 and 4 is only 1 unit, and similarly in case if you get a sample here whose sample mean comes out to be here 3, then the difference between 3 and 3 is exactly going to be 0. So, this is what we mean by the unbiasedness character or the property of the estimator. So, now let me try to take here a couple of example, and I try to show you that how you can establish that whether an estimator is unbiased estimator or not. You will see after some time that do you really need to know the R software, or do you really want to know that how to compute them in the R software? Let us try to understand these things. Okay. So, suppose let me take the first example where we said that let x1, x2, xn be a random sample from a Poisson distribution with parameter lambda. So, we know the probability mass function of Poisson is given by this, right. Lambda is power of x exponential of minus lambda divided by factorial x, and the range of x is the value 0, 1, 2 up to dot dot dot, right. Now, you want to know the value of parameter lambda, that is unknown to us, and suppose we propose that we try to estimate the value of lambda by the sample arithmetic mean. Well, that is another question, that how can you take such a call that whether lambda can be estimated by arithmetic mean or some other quantity. So, that part I will skip at this moment, and I will try to address this issue when I am trying to introduce the estimation methods. Right. So, at this moment you can just assume that suppose somebody has informed you that you can estimate the unknown parameter lambda by the arithmetic mean, say this one upon n summation xi. So, now we want to know that if I am trying to know the value of lambda by the sample mean x bar, then is it going to be an unbiased estimator or not, right. So, now I try to use the properties that we have learned earlier. We know that if a random variable has got a Poisson distribution with lambda, then the expected value of x is coming out to be lambda, right. Means if you cannot recall, you can just go to the lecture on the Poisson distribution, and there you will find this result. Now, I try to find out here the expected value of x bar, and now you know how to compute this value. So, that is going to be simply here 1 upon small n summation I goes from 1 to small n, and expected value of xi. Now, this expected value of xi is here lambda. So, now if you try to solve this quantity, this will come out to be n lambda upon n, which is here lambda. So, you can see here that expected value of x bar is coming out to be same as the value of the population parameter lambda. So, I can say that sample mean is an unbiased estimator of the population mean. So, now you can see here this is how we try to establish whether an estimator is an unbiased estimator of the population parameter or not, right. Now, let me try to take one more example. Suppose I try to consider that let x1, x2, xn be a random sample from a Bernoulli distribution, which was indicated by binomial 1p with unknown parameter small p. So, this is the probability mass function of Bernoulli distribution. So, now since the parameter p is unknown to us, suppose we propose or somebody inform us that p can be estimated by the sample mean x bar is equal to 1 upon small n summation I goes from 1 to small n x I. Now, we want to know whether this estimator is an unbiased estimator or not. So, we know from the properties of Bernoulli distribution, and that we also had understood earlier also, that expected value of x is equal to p into 1 plus 1 minus p into 0. Right, you can see here it takes value p when x equal to 1, it takes value 1 minus p when x is equal to 0. So, this value will come out to be here p. So, now if you try to find out the expected value of x bar, this will come out to be 1 upon n summation I goes from 1 to n expected value of x I, and then you try to replace expected value of x I by p, and this will come out to be np upon n, that is equal to here p. So, in this case also you can conclude that sample mean is an unbiased estimator of the population proportion or the population parameter small p. Well, in case if you try to take here something else, possibly this may not hold true, but that you can know only after doing this type of algebra, right. Now, just to give you an idea that not all the estimators are always an unbiased estimator of the population mean. Suppose I try to take one more example where I assume that the random sample x1, x2, xn is drawn from a binomial distribution with parameter p, right. So, we know that the probability mass function is given here like this, that we had understood earlier, and in this case expected value of x is going to be np. So, now in case if you try to take an estimator here, say delta x to be like here x plus square root of n divided by 2 divided by n plus root n, and if you try to take its expectation, this will come out to be expected value of x is going to be replaced by np and all other part is constant. So, it will appear as such. Whatever you do means you cannot say that in general this is equal to p, this quantity is not equal to p. So, in general means I can say that this estimator delta x what you have considered here, this is biased estimator of p. Well, in case if you try to take it here another estimator here, say theta hat is equal to x bar, you can see here this is the sample mean 1 upon n summation I goes from 1 to n x I, and if you try to take its expectation, it will come out to be here 1 upon n summation I goes from here 1 to n, and expected value of x I, expected value of x I is going to be here say this here n p. So, this will come out to be here p. So, you can see here in this case this sample mean will come out to be an unbiased estimator of p, but this estimator delta x is a biased estimator of p, right. Similarly, I try to take here one more example, and this sample x1, x2, xn is coming from normal distribution and whose mean mu is unknown, but variance is known as 1. Now, I try to consider here suppose different estimator, and then I try to see for their unbiasedness. So, I try to consider here this estimator delta 1 x equal to x bar, and then I try to see the expected value of delta 1 x, this comes out to be here 1 upon n summation I goes from 1 to n expected value of x I, and expected value of x I here is mu. So, this will come out to be here mu. So, this delta 1 x equal to x bar, this is an unbiased estimator of the population mean mu. Now, I try to propose that instead of using the sample mean, I try to use the arithmetic mean of the first two observation like an x1 plus x2 upon 2, and I define here another estimator delta 2x. Now, in case if you try to take the expectation of delta 2x, this comes out to be expected value of x1 plus expected value of x2 divided by 2. This is mu plus mu divided by 2, which is equal to here mu. So, you can see here that this x1 plus x2 upon 2 as an estimator of mu is also an unbiased estimator of mu. So, now you have seen that there are two estimators that are unbiased. Now, let me try to take here one more option, and I decide that I will use only the first observation to estimate my mu, and I denote this by delta 3x. Right. Then you can see here that expected value of delta 3x will come out to be as expected value of x1. This is also actually mu. So, now you can see here not 1, not 2, but all these 3 estimator, they are all are unbiased estimator of mu. Right. And similarly, if I try to take one more option, that suppose I say that okay, suppose I try to consider this summation I goes from 1 to small and ai xi as an estimator of mu, where this ai greater than 0 are some constant. Now, I want to know that under what type of condition this delta 4x, that is summation ai xi, is going to be an unbiased estimator of the population mean. So, I try to take its expectation and I find out here that this is summation I goes from 1 to n expected value of xi, and which can be replaced by here mu. So, now I can say that 1 upon n summation I goes from 1 to n ai mu is equal to mu. That means mu here is constant on both the sides. So, I can cancel this here mu on both the sides, and I can write down here 1 upon n summation I goes from 1 to n ai equal to 1, right. So, this is the condition that if this condition hold true, then I get an unbiased estimator of mu here. So, now you can see here, suppose if this condition is true, that we are trying to choose this constant in such a way such that summation ai upon n is equal to 1, then you can see here all these estimator delta 1x, delta 2x, delta 3x and delta 4x, they all are unbiased estimators of mu. Now, the question comes, which of them is a good estimator or the best estimator of mu? What would you suggest to a user that in order to know the value of an unknown parameter mu, which of the estimator out of these 4 estimator can be used that is going to give us a good result? So, that means we have to think something more, and besides this thing you can see here that the range of the estimators of delta 1x, delta 2x, delta 3x and delta 4x, that is also different, and in general that may be different for actually each. So, that means we need some more information, or we need to more criteria to be imposed on such estimation procedure, that only one quality, that is one property, that is the property of unbiasedness, is not going to help us. Right, we need some more qualities, right. Okay. So, now let me try to take here a very simple example, and I try to show you on the basis of our software that how does these things will look like in case if you are trying to establish that whether the property of unbiasedness holds for an estimator or not. Because in data science it is possible that you are trying to use an estimator to estimate any parameter or a function of parameters, and you really do not know, or it is very difficult to establish mathematically that whether the estimator is unbiased or not. So, in these cases we can use the simulation techniques, and we can have a fair idea that whether this estimator is going to be an unbiased estimator or not. Well, these results are based on the simulation, and these results will change from simulation to simulation, and every time you conduct this experiment, but more or less the results are not going to change much, so that you cannot be confident in saying whether this estimator is biased or unbiased. So, what we try to do here, that we try to take a sample from the normal population with mean, mu and sigma square, and suppose this both mu and sigma square are unknown parameters. Well, how to estimate sigma square, that we have not yet discussed, but I will discuss it soon. But here, because for the sake of understanding, suppose we propose that we are going to estimate mu and sigma square, and there are two possible choices. The first choice is this: I will try to take here mu 1 hat to be here simply the sample mean 1 upon n summation xi, and the estimator for the variance is sigma 1 square hat, which is 1 upon n minus 1 summation I goes from 1 to n xi minus this mu 1 hat whole square. And similarly, the other option I can say that instead of computing the mean, I try to compute the median of x1, x2, xn, and let this be my second estimator mu 2 hat. And based on that, we try to estimate the value of sigma square as here says sigma 2 square hat, which is I goes from 1 to n xi minus mu 2 hat whole square, right. So, notice one thing, that here I have not used any divisor here like this 1 upon n or n minus 1, this is not here. It is so simply the sum of squares. So, now we try to observe between these two estimators of mu and sigma square, how we can get an idea that whether these estimators are unbiased or not. Definitely, I am saying once again, the 100% confidence can be achieved only when we can prove mathematically, theoretically that the estimators are unbiased or biased. But in complicated situation, this simulation will help us in getting a reasonably fair idea. Right. So, what I try to do, now you know how to generate the random numbers from the normal distribution. So, I try to generate a large number of samples, and then I try to compute the values of here mu 1 hat, mu 2 hat, sigma 1 square hat, sigma 2 square hat, and then I try to compute the mean of those mu 1 hat, mu 2 hat, sigma 1 square hat and sigma 2 square. Right. So, here I have written this small program. You can also conduct it on your computer, but anyway, means I will try to show you it towards the end, but at this moment I will try to show you the outcome. So, here I am simply trying to generate say a number of observation, and we are going to repeat them for say some number of times, and whatever are the outcomes, they are stored in a matrix, and here I am considering mu equal to 10 and sigma square as 25, and then I try to generate the random observation from the normal distribution, and I try to compute the mean and variances using the estimators mu 1 hat, mu 2 hat, sigma 1 square hat and sigma 2 square hat, and then I try to compile the information. So, you can see here, this is the screenshot of the same program which I just shown you. And now, if you try to see here that when I am trying to use here this program, the first value here is n and second value here is rep. So, when I try to just use a sample of size 10 and I generate it only for 5 times, right, then I get here the values of here mu 1 hat like this, mu 2 hat like this, sigma 1 square hat like this and sigma 2 square here like this. Right, and you can see here that these values are close to mu equal to 10 or and sigma is equal to 25 or not. So, you can see here for this mu 1 hat, this value here is 10.26, which is pretty close to 10, and the value of sigma 1 square hat, this is close to 25. But for the median case, the estimated mu 2 is pretty close to 10, and but the variance sigma 2 square is very different from this 25. And if you try to repeat this observation, and instead of 5 times getting the sample, you try to take 50 samples and you try to compute the same thing, you can see here the values in the mean, they are not changing much. The values in the variance estimator sigma 1 square hat, they are not changing much. The values of the median, that is also not changing much, but the variance sigma 2 square is still very different from the true value. And similarly, if you try to generate 5,000 samples from the same population and you try to compute the same thing, you can see here that the values of here mu 1 hat, they are not changing much. The values of here sigma 1 square hat, they are also not changing much, or they are not deviating much from the true value. Whereas, if you try to compute the estimate the mu 2 hat, these values are also close to 10, but the values of sigma 2 square hat, they are very far away from the true value 25. And similarly, if you try to increase the sample size and you try to make the sample size to be here 100, and if you try to repeat it for say 50 times, that means 50 samples, 500 samples and 5,000 samples, still you can see here that the values of this mu 1 hat, they are pretty close to 10. The values of sigma 1 square hat, they are also pretty close to the true value 25. The values of mu 2 hat is also closer to the true value 10, right, but the values of sigma 2 square, they are very different from the true value 25. Right. The reason for this I can explain you theoretically also. The reason here is that in a normal distribution, the values of the mean and median, they are actually at mu, right, and the estimator, this sigma 1 hat square, actually this is an unbiased estimator of sigma square. That is why you can see here that these values are very close to the true value. Now, the confusion here is between this sample mean and sample median, because mu is the value of sample mean as well as the indicating the value of sample median, because in a symmetric curve mean and median are in the normal curve, they are lying at the same point. So, mu is also indicating the mean and mu is also indicating the median, and since the distribution is symmetric, that is why the value of mean and median, they are coming out to be nearly the same, and it is difficult to judge from the simulation that whether mean is an unbiased estimator of mu or median is an unbiased estimator of mu. The fact is this, that mean is an unbiased estimator of mu, whereas median is not an unbiased estimator of mu, but sample median is the biased estimator of mu. But by looking at this numerical results, you cannot really say with 100% confidence unless and until you have done the algebra or the mathematical proof. So, that is why these mathematical proofs are required, but definitely when you are trying to deal with a complicated condition, complicated situation, then definitely this simulation technique also give us a fair idea, right. So, means I just want to show you that whether this program is really working or not. So, I try to copy and paste this program. You can do it from the slides yourself into the R console, and I try to paste it here. So, and then I try to execute this program, which I have shown you the outcome over here. For example, you can see here, if I try to make it here, this program here. So, you can see here, once you try to execute it, this is trying to give you here these values. Yes, you can see here the first value is here, the means the mu 1 hat, second value here is the sigma 1 square hat, third value is here the mu 2 hat, and fourth value here is the sigma 2 square hat. And similarly, if you try to repeat it for say 500 times, then you can see here these values are obtained here like this. So, well, indicating or getting these values from the execution of the program is not a difficult job, right. But my idea was very simple, that I have introduced you the theoretical construct of a statistical property. Well, in case if you want to be 100% confident, you have to depend only on the mathematical theory. And this situation can be seen in real life very often. Suppose some of your colleague comes to you, and that person doesn't know statistics much, but that person is good in simulation. And suppose that fellow suggests that okay, the population is normal and one can estimate the mean by arithmetic mean, median, or say mode. That means get a sample, try to compute the either the arithmetic means of the sample values or the median of the sample values or the mode of the sample values. Now, when he is trying to do the simulation with this type of programming, then he will get the same values, nearly the same values. Some value will be 10, some value will be 9.9 or 10.1. So, practically it is very difficult for us to judge whether these three estimators are unbiased or not. So, now under these type of conditions, when you really want to be confident, you have to take the help of theory. You have to find out the expected value of sample mean, sample median, and sample mode. And in case if you are getting the value as mu, then you can tell your friend, well, these three are unbiased, but this is not going to happen. Only sample mean will come out to be an unbiased estimator, and sample median and sample mode that are going to be biased. That is a different thing, that the amount of bias is going to be less, and this is a very common thing which is happening in the data science. And that is the basic difference between the two, and that is why we are here to understand that what is the connection between the statistics theory and data science and its application in the data science. Both have to go along, both have to go together, they cannot be separated. And if they are separated, as I said in the beginning, that you will not become a doctor, but you will become only a compounder, right. So, that was my idea. This is how I wanted to present this topic. But definitely there are many more distribution, there are many estimators. I would request you that you try to pick up a book, try to look into the problem, try to take the problems from your assignment and try to solve them. And I am sure that now you should be convinced that why theoretical foundation of statistics is needed to understand the intricacies involved in the data science. So, you try to think about it, try to practice, and I will see you in the next lecture with more details on consistency of the estimator. Till then, goodbye.